involved. Trying to work out, but actually the group has areas, although it's so this used to be the place where it's big transformers from stations were built in. As you can see, there has been railroad track entering the building here. That's also why the so big, big train here. We took almost a year ago here. This is in several locations and very quite for new building for these occasions. Yeah. So environment to better a and also accommodation here is wonderful. So we as so says it's video image. But that's it's slides are also so here. And then it got so one of the to use vision is with energy transition, but also the problem here. And hopefully that we are able to solve with solutions. So we put in that your schedule here also line up and then you with yeah, set this challenge we bring software and us in fixed. So to take a little bit what we're doing next is that is similar like staying at Allianz, we have a few small ones. So what we see with the execution of the energy transition is here in optimal choices because there is not one solution that fits all. We're not definitely we need to make optimal energy choices. Some choices made by customers, and we have to deal with them. But the other thing, and that is really, and that's what we stated it. Mostly on the local like in the neighborhoods, we have not experienced yet a broader outage, for example, throughout the whole Netherlands or even worse throughout Europe. And we have less than 17.5 minutes of outage within an access. I think that qualifies us as the best DSO worldwide. Just to give you an idea. That is also a problem because we're not used with outages. And I actually mentioned it last week when I was with all the listeners of an access at an offsite location. It's like with IT. Sometimes it's really good that you have an outage with IT because then everyone understands that why it was so important to use it and that it's needed and that you have to have a sort of an uptime guarantee. And what we also have is, okay, customers need to know what they are going to encounter. Because normally it was, okay, you get an order, we get an order in, deliver us X, Y connection, with this power setting, and we deliver that within a certain time. Nowadays, those time periods are totally closed. For example, here in Brabant, that's the way we currently are, so in Limburg, and that is spreading out towards the rest of the Netherlands. Companies that want to have a power connection, new or a bigger one, need to wait between 5 to 10 years. The good thing is we're very good in predicting when that will happen. Small anecdote here, and that's what our CEO brought a few months ago. Some connections are really expensive, and then he has to sign off on that. That's above €1 million. And then he got sort of, okay, this is the offer for the customer. Yeah, the big company, yeah, more expensive. Yeah, okay. Okay, more than $1 million. Yeah, that's fine. Delivery date, October 1st, 2031. That must be a mistake. So he went back and said, no, it's indeed October 1st, 2031. That is what currently is happening in the Netherlands and also in other countries soon. So we have a new reality, as we call it. So since the outbreak of the Ukraine war, not only energy prices raised, but also a few other things raised. Also material, to get cables, to get equipment, to install that, that has become a hassle. It's getting less and less now. And what we see now is that due to the higher prices in gas and also electricity, people are going to generate electricity themselves. That is really cool because that helps the energy transition, but that causes also a problem. Bigger customers, companies are switching from gas to electricity because it tends to be cheaper, so they swap that out. But then you need bigger connections, bigger cables, and that's where the problem starts. Because if you can't get them, you can't go through the transition, etc., etc. So we have to tell customers now, and that will be also towards smaller customers, like new built houses, towards families that are building a house where there's a new project where like 1,000 houses are built. Then we can't connect those houses. Our colleagues have that in Almere, but we as a Nexus are also encountering that we have to disappoint people in saying, okay, we can't give you a bigger connection, or we can't even give you electricity. That's a new interesting fact, and becoming worse and worse. So what we need to do, and that's also where prediction models come into play, is, okay, it's like waiting for the train that has a delay. It is not so much a problem, to some extent, that there is a delay, but you want to know how long it will take, because then you can do other stuff, or you can anticipate. And that is what we're currently trying to give to customers, business customers, but also end customers in homes. What is the expectation? Because that is more important than saying you can't get it, because that is not really helpful. So what is and I don't know if you all are really familiar with what we call congestion that we have on our networks. So it's not only us, but it's all the DSOs in the Netherlands. So what is the issue with the congestion? These are pictures of June or July. I need to check, but I think it's July. It's the congestion on electricity. And as you can imagine, there's the red bars. So that is here. The red bars, that's not good. Whereas yellow, it's so depends on where you are. And if it doesn't have color, then it's pretty okay. And that is what we call afname. So that is getting from the grid. Where it's red, you can't have more from the grid. It becomes even worse when, and that is also not new, but it's expanding very rapidly, is feeding into the grid, like with solar panels or other ways that energy is produced by, for example, homes, solar panels, but also businesses that do that through heat conversion, etc. And there you see that the Netherlands is locked, more or less. And what that means is what is locked, because there is not a clear understanding with everyone, but why is it locked? And it is locked, and you can actually compare it a bit with traffic and roads. So if you compare a car to power, a kilowatt, and if you compare the roads with the travel that the car needs to go, then we calculate our network based on, okay, what is the maximum that the network can hold until there's a traffic jam. And then calculate back, okay, if you have a car, you have a car, and you have a car, we expect that you all drive at the same moment. And that's how we calculate our networks. And there's only one thing that is not possible on our roads, our electricity roads, and that's traffic jam, because traffic jam will immediately be an outage, a blackout, small, big, but that's with traffic jams. So what you see here is an administrative calculation on what maximally, if everyone would drive in the Netherlands, would be on the roads without it. Yeah. So if someone says, I'm going to buy a new car, then we say, but you can't buy a new car because your house is near a road that has no capacity anymore. But if you look, for example, in the middle of the night on that road, no one is driving. But we need to calculate with all the capacities added to each other. That's the biggest thing, and that's also where you come into play. So what we're currently looking at, this is a graph updated to 12th of June, so that's almost, that is half a year ago. You'll also see a small arrow, but we'll point out where that is. So if you see, this is Q2 this year, and this 2108 needs to be there, and 1942 needs to go down, is that if you look at the pink line, you see that the requested power is more than 2 gigawatts. That's where I said, okay, bear in mind what we're building each year. So this graph is only rising, and it's rising steeper than we can build. So the problems, that's where 5 to 10 years comes from, can actually go up to 15 years or more, worst case. So what we see is that we cannot build, simply cannot build in the Netherlands what is requested. On the right side, the graph is feeding back. And if you look at the figures over there, then you see that 16 gigawatts is requested to feed into the grid. That is not possible. If you only build 2 gigawatts a year, then you can imagine how long it takes to shove that backlog away. And that's the reality that we're currently in. So, is there then only a doom scenario? No, there's not. So what we do is, and you see that on the left side, is that we're growing in what we can build. We used to spend roughly 800 million euros a year on new investments, and we're scaling that up. We can only scale that up if there is certified people that can actually do that. So we're also training people to be certified to create new delivery. And we're scaling up to 2 billion euros only with our diesel only per year. And we need to continue that for the next probably 20, 25, 30 years. So we need a lot of people, a lot of material, and we also have 2 next problems: permits. Because What you see there is that those transformers, new transformers, big transformers, new transformers, need to be put somewhere. So we need to build those small electricity houses that you see in your neighborhood. And we probably need to add 60,000 in the Netherlands. You can imagine that no one wants those electricity houses in their neighborhood because, well, they're not really nice, but you have to do it. They need to be there. And then, so with the local governments, you need to make permits. Can we build that there, etc., etc. That takes time. And each day that those permits are delayed, that is one day later that the energy transition for that neighborhood is done. And the second thing is, and that has to do also with the environment, is probably heard about the six issues that we have, so the nitrogen issue that we have with our environment. If we dig holes with machines that exhaust nitrogen oxide, then you have issues because you need a permit for that too. So also there we go to electricity, but that's going gradually. And then the last thing is also very grounded because all the cables, glass fiber, coax for television, gas, electricity, etc., it is really close to each other, including water pipes and sewer in the faces. So how do we actually dig into the street while not interrupting the other services? So what are we working on? With grid models, we're here on the left trying to predict, okay, where is the congestion going to hit us the hardest? The second thing is with solar panels is that we need a bit of a change in the law for that too, is that we can say to big solar farms, okay, stop producing, curtail it. You need to power down because if the sun is shining the brightest, of course, it's the biggest return on your investment, but that's hurting our nation because it can actually provide blackouts. So we need to do curtailing there. Then we have group ATOs, and that is a sort of a contract that you, with a lot of companies together, form. That's to say, okay, we want to have a big connection, but we're going to share on paper this connection. Because if my neighbor is only going to use the power he needs from 2 to 3 in the afternoon, and I'm only needing it from 8 to 9 in the morning, then there is no collision. So there is no congestion. But you need to put that in writing that everyone on that contract sticks to what he is allowed to use when. And of course, if they want to then use the power in the afternoon because they changed their business model, that is then not possible. Because then with your neighbor, if we add up, and then you have a congestion. Currently, what we also have suggested with all the TSOs in the Netherlands is what we call non-firm ATOs. So that means that if the law changes, is that especially bigger businesses need to come forward when they are using the energy. How much power, how long, etc., to flatten that curve and to actually have insights in when they are using it. And they can't go out of their boundaries because then you will cause an outage. That is the only way to allow more vehicles on the road. If you can agree, okay, I'm driving from 8 to 9. If you can drive from 9 to 10 and the other one is from 10 to 11, then there is no traffic jam in that. And then batteries. With batteries, there's also something fishy. You would say, okay, but that's perfect because then on a local grid, you can actually stabilize everything, your frequency, your voltage, but also demand and request. You can locally do that. And what you see with those batteries is that they're currently pretty expensive, and there is a business model behind it. So if you expand on the business model and to make more money, you're actually creating more congestion. Because if you say, okay, I'm empty now, yeah, now the prices are cheap, and then sort of bulk load the battery, but that is then also a congestion issue. So we need to work also with agreements there that they use it actually in our advantage. And that is hard because you will make less money with the battery, and that will make your return on investment later. So, I'm going to stop that. 50. So this is to give you a bit of an insight in what the current struggle is with the DSOs. I think most of you, probably if you have read the news, you've already seen this. So what are we as a Nexus doing there? For example, work together with you, work together with the other DSOs. And that is why Alejandro sent me an email and said, can we have this session here? And I said, yeah, come on, we'll arrange it. And then we tour. And that is something that we're doing more and more and more, is that we work together. That is not something we have done over the years, because every TSO is their own company. It's an NV, as we call it in the Netherlands. They have their own responsibility, their own profit and loss, etc., etc. Only regulated. And then we said more than 2 years ago, okay, why aren't we going to work more and more together? Let's find out if we can build, if we have an issue and we have found a solution, we build together the wheel and make it together as round as possible, instead of figuring out how to build a wheel 3 times and also make it rounder and rounder over the years. And then you have 3 wheels that are more or less doing the same, but it took you way more work, way more time, and way more resources. And the last ones are really scarce. So what we have introduced is that we started working together with the 3 big DSOs in the Netherlands, Stade in Alliander and the Nexus, and we built that actually out. So we see now that things that we need to build together, you see immediately the first question is, what did the others do? And can we, as we call it, not steal with pride, but copy with pride? So make things, for example, open source, and even the things that we have developed ourselves, or at Stade or at Alliander, we ask, okay, can you open source this? And so we are starting together, and of course it is specialized software from time to time, open source it, and then we can use it from each other. Because there's one thing that we can't, that's also something with regulatory, we can't sell things, we can't make a profit. So if we develop something in IT and we want to sell that towards state, then the law says you can't. And if you make it open source, and literally that is what happened a few weeks ago, people from Stadium, for example, were over here. And they said, okay, you have a really cool prediction model on XYZ, and we have the same base software. Can we copy the software? And we almost literally put it on a memory stick and it took it home. And then because we just said, or I said, because they asked, can we do this? Yes, we can. Make it open source. It's now open source. We own the IPR. And it's open source. They copied it and they're using it already. That saves a lot of time and a lot of resources. And actually, the good part is it's so much more fun. So that's what we're doing now continuously. And we're making this bigger and bigger. And the update from that is that we have an organization and it's called Netbeheer Nederland. So that's the organization that is about the TSOs. And the TSOs, not only electricity, but also gas. They wanted to have an enterprise architecture community. And I said, yeah, I'll share that. Come over here. And I thought, oh, that will take years before that's there. And as I explained lately to them, it's like putting a flare into the mountains because an avalanche came down. And I had to run through the snow because all the TSOs said, yeah, here's our DSO. What are we going to do? What are we going to develop? And when I said, okay, now let's make it challenging, we're harmonizing all the architecture principles. Yeah, agreed. So everyone sent in their architecture principles, and there's now someone sort of aligning them so that we can then have one statement. Okay, these are our architectural principles. So if someone at Stadium is going to later on build something, we can use it too because it seamlessly fit within our architecture. How simple can things be? What we're also doing is not per se on congestion of other things, it's also on safety. As you saw, starting of this meeting is safety is number one, not only with us, but also with the other DSOs and TSOs. And for example, we're making now a safety app that we can use throughout the Netherlands in high voltage environments where everyone sort of can check in and say, hello, I'm working here. Don't switch on the high voltage. I don't know if you have seen the high voltage environment just here outside. That's, by the way, not from us, but from Tenet. You don't want to walk there if they switch 380 kilovolts, because it will fry you alive. And so those kind of developments we're doing now together. That was a few years ago sort of impossible actually to bring forward. And then open source. I mentioned it. We can create open source. You can create open source, but also together in the world, we're creating open source. And we are now advocating, use open source, make it better, contribute, use it, and that will all make us happy. And it's also very cost efficient. That is also what we're looking for. So the first thing is we ask ourselves, what did Steden and Allianz do? And then the next thing is this available in open source? Yes. And then we start using it. And the last resort is buying and completely make it yourself. Because that takes a lot of time. Are there in the meantime any questions from the audience here or the audience online? I'll come to you in a moment. Just checking. No, then people can start thinking of a question, but that's yeah. This repeat the question is called the So, what's your question? Organization. My question is about what do you see as the major challenge of the long-term NATO? Is it just a legal thing that has to go through the energy of the electricity that then it becomes possible, or do you see other short offers possible? Yeah. So the question is about the non-firm ACTA. Is that only a legal thing that needs to raise, or are there hurdles? So is that correct? So first of all, since it's a legal thing and only the government can change the law, especially given the circumstances where we're currently in the Netherlands, where we have just a new House of Parliament, but we also need to form a new, not a new government, but a new cabinet. You see that things related to this tend to slide in time. So I see that as a hurdle. So that's one thing. So that's a hurdle. The second thing is this is there are four non-firm atoms, and they as a solution to our problem. But the thing is with solutions is not everyone is happy with that. So what you will see if this really comes into play, companies will say, but then we have another administration that we have to use. We have to do integration in the view to get data. We need to have an IT environment that calculates when we can do what. And how do we deal, for example, with fines? Because if someone is naughty, and we can measure that, then we say, hey, you have a contract here. Do we then need to go to a judge, for example, to say, he was naughty and now you need to punish him, and where's then the money going? So the hurdles there, this is an ideal situation. But the hurdles are, okay, how to implement that. Because if this becomes law and all big companies with certain connections need to comply, it's the same with environmental things. Sometimes we say you can't exhaust more than X, Y, Z on these things, like CO2, but also other things. What happens if they don't? Yeah, you get fined.
Just to add on the point, because you said it's about compliance. When you set up these rules, then you're not free on the energy company. You have account on a power basis with a relatively short time frame. So what I hear from you is these compliance are not yet fully defined to the minimum level. You have to define it. It should be waiting 15 seconds because you should allow some control system to take actions. And the second is that what I see that from the business point of view, the third article with a clear merchant with model, right? That you have a third article, you know you can use this, you can produce the goods, then your wings for this kind of a picture for profit is very clear. Both of the assets is actually built for say 25 even to 40 years. Then the question is, we could have two changes. We made a non-firm article. We have certain time stint where we take the power either full amount or half of the amount with the next hour. We set up this kind of rhythm over the years or over the weeks that you have this kind of low profile pattern. Like you said, over the years, this will change, but over the years, your congestion rate will also change. How do you actually resolve this? That's the mechanism that I'm looking for this non-firm article. When the external environment, the pre-congestion changes over the course of 40 years. With the business also changing in the sense that, yeah, they have a different production source of the resource better. Will there be a mechanism also from the non-technical side that you see, okay, you can renew this every year, but that also creates a very big uncertainty on the business side?
Yeah, so to rephrase your question is, okay, how well are those four non-firm atoms already detailed? That's one thing. And the second thing, you're saying, okay, the behavior on the network with the companies related also to the non-firm atoms will change over time. So how do you use actually the future?
The investment is at the time there's a prediction on the behavior, but in reality there's a change of behavior. How we bridge that gap?
As far as I have read it, to state your question is, okay, so how will that change over time? Because there's investments related on business sides, and how will they be earned back? In all honesty, I don't know. That is not described. So this is a suggestion that has been made from out the DSOs towards the government, saying, okay, if you on a short term want to do something, we need a firm grip on something. And here you can mix and match only four principles as a company, and it is up to legislation to say to the companies, and you need to adhere to this. There are the only winners are we as the Netherlands, and the winning is in the fact that the lights will be kept. So you can say, okay, we're not going for non-firm atoms because it will take a lot of money because we need to adjust to it and to adhere to it. For the last one is the biggest thing probably. Or we say to the other companies in the Netherlands, stop investing in the Netherlands for the next 10 to 15 years, because there is no power for you, because the other companies have consumed it on paper and are not willing to change because they have to invest. So it is a burden that is for all of us. So and the only thing we are here is to keep the lights on. So for us, it's pretty easy. We say, okay, this is how you can solve it. But there is no upside to this, besides the fact that the lights will be kept on. That's the toughest one. That's the tough decision that we have to take. And that's also the tough decision that has been not firmly been taken. For example, in solving that we know for solar panels at homes. We know now probably that as of 2026, in steps, it will degrade. And there you see already that customers are saying that are wanting to invest in solar panels, saying, yeah, but the business case is getting slightly worse, by the way, slightly worse. But besides you, not all the people are that handy in Excel, they can do the math themselves, but they expect to win back now the solar panels in 4 to 5 years. But what is wrong with 10 years? From a principal point of view, there was a time that it took 25. So be happy. And that's the thing. So that's also the mindset that's needed. And that's coming back to the earlier thing that I said is perhaps it's a good thing that from time to time the power will actually go out. Because then we realize again, it is also me that needs to do something to keep the lights on. And it's not the DSO that will keep the lights on. Because our way of keeping the lights on is saying, stop, we're building, and what we can expand, nice. And for the rest, we say, you can't get it. A new home, a new area, sorry, no power. Suit yourself. You see the catch? Yeah.
I have a question about the open source architecture you were talking about. I was wondering, I think it's a great work together with DSOs and developer and the other. And I was wondering, what are you planning to facilitate this open source architecture?
So the question is how as DSOs we're going to facilitate the open source architecture. I would say in threefold. So first of all, we're open for it. That is also new. The second thing is we're going to sponsor it. If it's with food or even with money or with whatever is needed. So we're supporting that. And the third thing is we're giving an example. So we're also doing it, using it ourselves. It was unimaginable 2.5 years ago within Nexus to use open source, although we use Linux, but let's forget. So, and we needed a workflow mechanism, and we used an open source workflow program, and everyone's like, open source, yeah, but there is negative sides. Yeah, I can call them too on closed source or commercial off the shelf or build it yourself. And we went through towards open source. Done. And that's the same almost for other DSOs now too. And Alliander has already created an OSPO, so an open source program office. We, as of January the 1st, are starting an OSPO also with the Nexus to facilitate open source, create open source, share whatever is needed. One interesting is last question.
I am it's development scale of development, and I was wondering, you talked about these issues with all running something real time control of assets. What is the development with regards to open source software like that?
Okay, so the question is what do we build open source for real-time steering networks?
And then steering the assets.
Steering the assets, yeah. So what we have in our network internally, that's called the OT network, so the operational environment technology. The whole measurement network is called DALI, and we have software behind it. It's called software, as you can do math. And DALI is hardware that we are putting now in a lot of our stations to monitor the network and get the data out of the network. So literally how much current is flowing there. and to see what on transformers the instability is, and monitoring a lot more stuff. And based on that information, we do also switching and routing and those kind of things, and also knowing, okay, it's going wrong here pretty soon if we don't do anything. So is that open source yet? No, but we own the IPR. So one of the things is that we can make, to some extent, can make that open source because it's ours. So that's what we're going to do. I think what answered your question a bit more is that the steering mechanisms, we also need that on business, on bigger companies, steering their heating of their buildings, steering their power plants, steering the machinery that they have. There they need, based on information from our network, that they're knowing also from those non-formatos, okay, now we can pull power. It's battery, or we can pull power directly, but also switching on and switching off gradually in bigger machinery, for example, and not on 8 o'clock in the morning, just with one big switch, start everything up, and you have peak power issues. So that's why I think software will be used, also open source, because companies do not want to spend much on it, where they will steer their internal business. That's my gut feeling. And that was then last question, last answer. If we continue on the career. That's now. Thank you. Our colleague from Access present the activities of how we work. So, can I floor is yours?
Welcome. I'm here on behalf of the neighborhood. And today we're going to tell about how we use Hungary. But as everyone before us said, safety first. So I'm going to we are both in neighborhood. What we do is use input from municipalities and all the plans for the energy transition, we translate that into impact in the next district. Jimmy is going to tell everything about that in a bit. So I'm Kenneth, I'm 31 years old, I've worked for Affiliate, outsourced mostly for the municipality. So I've worked at State on the other, and now I'm working for the last 1.5 years here at Texas, in the network. As a software engineer and technical team. Now that I'm coming into this himself. Yeah, my name is Jerry. I work at the Nexus now for almost 3 years. I also graduated here. And since 1.5 years, I'm partly in the energy transition. That's a team of experts tries to predict the future, basically. And I'm partly working as business analyst at Meetup. And we were very asked by guys from Albert Model to give a short presentation about what we do with Albert Model and how we use it. So what we do as a team, we try to predict future network congestions in our medium voltage network. That's what I'm focused on today. I'm going to share a short first we're going to talk a little bit about transition. Hopefully you all know that. About the electricity network layout, so how it's operated in Netherlands. Kenneth will talk about calculating impact, a bit of the network planning, and what we do with the results. So first we're going to the first two input, first two boxes, the input and prognosis. That's what my other team does. So not taking gained over my experts lead. Due to the climate change, there's a large electrification trend. So we have now a fossil-based society building shifting towards an electricity-based society. So think of heat pumps to heat your homes, vehicles to drive cars. Industry is changing from gas powered operations to electricity powered operations, and all that will have an impact on electricity. And within our team, we have more than 60 different drivers that will happen during the energy transitions. That we see also solar panels, rooftops, but also land, wind, the change of electrification industry from we have a lot of AC drivers, also heat pumps, heat networks. We all try to model that and make a forecast from around 2050 on how much energy will be installed for that project. And all those roofs are installed on different network levels. So in low voltage, medium voltage, high voltage. The residents are in low voltage, separating all of those in low voltage networks. Large rooftops for the medium voltage network, and all of those in medium voltage networks. That's why we get those input from municipalities. We are active talking with them, getting input from them on the neighborhood level. They tell us what the district plans are. So the district is going to use electric heat pumps. They're going to use a heat network. That's the input for our proposals. And next to that, the Netherlands has a national studies on what will the energy mix look like in 2050. There are 4 different scenarios. I'll mention all right now. One is based on a local, lot of local generation, and one is based on a lot of international generation. All those will have different impacts on our electricity grid. And that's just the team of experts who will translate this to a neighborhood level also, which we can use to calculate the impact. I'll give a short introduction about how the electricity network is operating. I'll keep it short because there are a lot of details here. So there are 4 voltage levels. You have extra high voltage levels. Those are operated by tenants and TSO. And you have distribution levels, so medium voltage and low voltage, which are operated by NXS, Allianz, and we, as PMA, will try to predict the impact on the low voltage and medium voltage networks. And for this presentation, we'll focus on the medium voltage networks. So the medium voltage network can also be further divided into transmission and distribution part, of which the transmission network carries the most of the electricity over the longest length, and the distribution parts will distribute that energy towards our customers. And those networks have to be calculated separately from each other to coincide with load. So on the distribution level, you have a lot of customers, which are likely, you have less, sorry, and in the distribution level, you have less customers connected, which makes the chance of an equal peak at the same time more likely in the transmission network. So if you have 10 customers, it's more likely that you have 10 at the same peak or at the same time peak. As in the transmission network, you have like 100, so the chance of those coinciding is less. So that's why you have 2 calculations. You do 2 calculations for the medium voltage network. Calculation impact of the electricity grid. First, you have to know how does that grid look like. There's another team in the Nexus that's automated generation of our network, and we load that in. So we get all the nodes, we get all the cables, transformer on those sources, and more. And we try to transfer that to a power grid on the network, in which we just load that in, and then we can add the loads to that network from a power grid calculation. And that's how we remember the loads, so we explain what can.
Yes. So as you can imagine, aside from the schematics, so the logical, the cables, and all the assets, you also need certain loads in the network. You need 2 different types of loads. The measured loads, in our case, you need estimated loads because we don't have measurements everywhere. We started to get more and more measurements, but we don't have the measurement system yet. The things that we use for measuring are mostly large-scale customers. Large-scale customers usually have measurements, then we try to do service. But also a lot of households, some of our households, they don't have measurements. So we also need something for that. So what we do for that is we try to estimate those. So what we are trying to generate is in worst case, because we want to invest for the future, we want to invest on near worst case, not so much worst case, because if we invest on worst case, then we would have to invest everywhere at the same time. And that's just not possible. How we do that is we use a bottom-up method, so we use only a few parameters, like how much electricity did this house use here, and choose simulation time, where we try where we try to approximate what the load is for a certain household during the day, summer and winter. We need those current loads to be able to estimate what the future looks like. All the drivers that Julie was talking about to plot those on the households. And there's a bit of overview of that here. So what we have is we have a bunch of scenarios for drivers. So how many? You understand the 4 scenarios. And for every driver, there's a bunch of adoptions that need to happen in certain neighborhoods. And we need to translate those neighborhoods level adoptions to asset level adoptions. So certain neighborhoods have more assets from the next thing than other neighborhoods. We need to translate that. So we do an estimation of where the impact will be. For some, we just do it linearly, so how many assets are in our environment and we strategy elements all those assets. For some others, we have a bit better of an idea where that options will happen. Say for the solar panels, we know that in richer neighborhoods, it's more likely that there will be solar panels there and poor neighborhoods. So we use that information to try to give the adoptions the right place in the network. That's mostly happening on low voltage. So on low voltage, we have to, because there's dispersion models in English. We determine the base load, and for all the future loads, we try to use the modeling technique of Scala to make sure that adoption segments the right places and to the right loads. And all those loads we then feed also into a medium voltage network. For the medium voltage network, there's more measurement data available. The dynamics that someone was talking about, we try to use those. And what we do there is we don't want to simulate every day of the year, but what we also are trying to do there is get the near approximation of near worst case. So we take certain percentiles of measurement data that we found well for estimating anything, and we take those as the base to then apply all the new profiles for the drivers. So I'm not sure what that comes down to is we take 15-minute load profiles for the customer connections and for the net stations. The net stations are the zealous transformers of next. We take those 4 scenarios, so high demand and high generation scenarios, and different scenarios for energy and speed due to coincide. And we take the driver profiles, because every driver has their own unique profile. So solar panels have a very different generation profile than, say, heat pumps have for usage. And doing that and taking all those, we have to do a bunch of calculations. And that's a nice overview of why we need to use this in the cloud and what the difficulty is for us in managing this. Because within the next graph, 124 medium voltage networks, we have those 2 scenarios. We have 2 different levels, so distribution and transmission networks. We have 69 timestamps for each of those. So we try to do 1 representative day in the simulation. And for drivers to 28 years in the future. So that comes down to about 1.3 million simulations if you want to do everything. And in a bit, we'll talk about redundancy operations because it's very important that redundancy is also factored in. So, and that is about, we estimate about 250 million. So that is why we need a big scale operation, big cloud. What we currently have as a view for that is to do that on AWS. So our current studio is already based in AWS. And what we want to do is probably use one cloud computer to the network to do the calculation, and then store that all on a data warehouse. I've heard that some very smart people from the other ISA that are also doing something similar. So I invite them for during the call to come to us and discuss with us about what we are doing. And then end users and applications will have views on the data warehouse. Yeah, that's also with why we use Power model. We want to use develop this locally. Used to have a cloud solution where we do all these calculations, but for us it was hard to develop it. And with Power model we can just develop it locally. It's scalable. It's transparent and open source, so it's not a black box solution that you buy and you have no idea what happens inside. So that was very important for us. And it's an active development. Every time we come up with a feature, it's already there or nearly there. So we're very happy about this. And then Jody is going to talk a bit about what happens with these results with internet.
Yeah, network. So what happens with those results for real-time connection? In short, it's basically is used for can a lot of customers be connected? Just where I can also most of that. But yeah, for a lot of services also, how much do we have to invest to make sure that the whole way of 60 gigawatts can be connected once if we don't have to go back to 5 years to make another cable, more transformers. If we invest, we want to do it immediately after 2050 and don't want to combine plus our assets. And it typically lasts up to 50 years. And still change throughout about 5 years. So we do 2,000 operations. We do our normal operations. That's how the grid is normally operated. We do that from current check up to 1050 for the first semester, that's fine. And it results in a cable level and those voltages. And then those are out of bounds. It's a high priority to invest in that network. However, our network has to also be operable during N-1 situations. So one cable has to be able to fail working on the maintenance, and our network still has to be within our limits. So we have to do a lot of calculations for that. Each cable has to be taken out once for each network. And we have to perform a new power flow if all the if everything is within limits. We have to store those, but also with the cable back and then the next cable has to be built and taken out of operations. As kind of summary, this will take up to 1 simulation, building simulations. So it's very important that we make some simplification for this. As of now, we don't really know anything. We make simplification in the distribution network. Let's take out the first table instead of the whole one. This latest a lot of simulations already. Still stays up 400 billion. So we still have to think something better. And what happens with those codes? So if the network is still too much code, it's overloaded like possessions. So we could and as I already said, some spatial necessities. So when we know we have to invest in a place like that, like transformers in the neighborhood. And also already those municipalities. So, in which the results of which years now for in which year industrial investment has to be greater. So we need to invest everywhere, but some places a little bit sooner than the other places, and so much greater. And before we even can invest, we have to go to the municipalities and say, we've got to lay 20 kilometers of cable here, place 20 transformers, we need some permits. Well, that takes a lot of years, and so we have to get ready. We have to start already for permits in 2030 or something. And we have to prioritize because people are scholars. We have to prioritize our investments. So, which investment will connect the most people or most customers to our network? For now, this is a lot of manual work from our colleagues at the grid management department.
but we are one solution in that, using boundary model, basically. Yeah, that was, and the last thing is what we're going to develop next. Mainly, we are going to use little cable loading at the moment, but we also use the network, the voltages. Voltage regulations, that kind of stuff. We want to calculate more scenarios, and we only use one scenario as one of the simulations. We have 4 different scenarios, so we want to do it with computers, but and shorter calculations. But we heard today it's already possible with this boundary model. So that's if there are any more questions, feel free to ask them. Did I get one question?
There's a question on that. Other than just asking, how do you regard the tab change the settings in power flow, especially the ones regarding automatic tab change?
Because automatic tab change is something we are going to address in the future. And how can we know, like, currently people running automatic tab changes and they're in boundary model. So after that, we're going to also try to implement that. But we do have most we set one voltage line for our whole networks. Once it's still for whole network, I get this optimized, but it's also just within the regulations of our grids for free. So we usually set that. It's quite a lot of it. We're going to start here.
Yeah. So are you comparing your estimation of the loads with the behavior for the grids for which you have the behavior to make sure that your estimation is closer to the reality?
So the question for the people line is, are we comparing our estimations to the measured value data? And the answer is yes. In a low voltage networks, we actively compare our results to the value. To make sure that we overestimate or underestimate our calculations. And after that is approved by the business, we can do that and we can go get questions.
What's the difference between the overall and of course our vision cloud solution?
That's a question as well as the difference between our model and vision cloud solutions. Basically, all of us, both like balance mode calculation. However, we try to do it locally, offline. We want to scale it up and make cloud solutions. Basically, we can't really develop ourselves. We have to send all data to an external partner. So we try to keep it in-house a bit. There is our thoughts are really most solution behind it. We use that as well. But for now, we haven't developed it ourselves. So
I think excellent analysis, lots of calculations. I wonder, can you share some insight because we talk about congestions. This is partially about congestions. But congestions, there are 2 dimensions. One is temporal. So what is the congestion we're looking at in terms of is it a daily cycle congestion, or is it a weekly, or is it seasonal? Then the other one we're looking at is it spatial. So do you see congestion more in the low voltage, or do you see the congestion more at a medium voltage, or do you see the congestion between 50 kV to 110 kV in these locations? So that I want to hear if you can share something.
So the question, there were 2 questions. I think the first one answer, but the second one is where our investigation is basically a network. So I know those will be what's titled. First question was
is the congestion more daily cycle?
Yeah, when is it not guess? So where there's some peak hours. What we see on simulation is basically right now we get due to like the biggest congestions during summer, during generation. At the moment, we have like 5 gigawatts of demand and 1 gigawatt of generation network. In 2050, we'll have 50 gigawatts of generation network. So that's about 50 higher. And most of those will be on low voltage networks. Well, a low voltage network will transmit to medium voltage, so that will follow quite quickly next. So everything that is low voltage, because medium voltage, but a lot of power is going to be there as well. So those will fill for adjacent. Pretty much on for that. And our high voltage are extremely transformers are currently bottleneck. So when those are replaced, or the best is that hopefully some of the adjacent will be.
When you say the generation, you actually meant those solar panels. You follow also like a day cycle, like the start at 10 o'clock, where people at 4 o'clock in the afternoon, then that's a bottom-up congestion that you see from low voltage directly propagate into the medium voltage, and then also stress your high voltage from medium voltage transformer. Is that a kind of analysis?
Yeah, so today yes, building the sun, and that is challenge factors. We only calculate the worst case days, so we don't really know whether it's a weekly or that kind of stuff for India. We do two generate one worst case generation, one worst case demand, and those worst case generation is to be between 6 o'clock evening, and during the month it's mostly when the business is up, so between 8 and 18. Mostly the demand or the festivals.
Yeah, but I think that's.
My question was, is the simulation, does it work at the level of individual observations which get generated and added for each pathway? Or do you work at the distribution level where you say, oh, we've got this is normally distributed and we can add it to the second normal distribution, and because they're reasonably close, we can approximate that as the third normal distribution, which allows you to skip 100 individual calculations. So does it work at the observational or at the distribution level?
Don't really understand.
I'm sorry, my background is in statistics, and this is about the computational shortcuts, which can often be used when you've got to calculate large groups, distributions of values which depend on each other. But I'll talk to you in break.
Yeah, that's like the question.
I'm sorry, I forgot to the people who are listening.
Time for one last question.
We have one more question. Cool, it's not just the short version, all right?
Well, we're going to relate it to this regarding the uncertainty because you're looking at very long-term future scenarios and all of things can change. How do you account for that in your investment decisions or your models or populations?
So the question is how do you account for uncertainties in the future for our providers? That's quite difficult. And actually has the proposition of we invest for the worst case, so that we always ready for it. So in a low voltage grid, we invest on the all electric scenario. So every household will have an automatic heat pump, has private EV chargers, and will have solar panels. If we go to a new network, or if we go to a network now, we put in the cables, we put in the performance for that scenario. If something else happens, yeah, tough luck for us, but the grid is ready for it, so we don't have to come back. Really, yeah. At the moment, we are more optimizing towards our people, our resources, than to money. So how do we take in the uncertainty of the future? Well, we try to minimize it by just taking the worst case things. Make sure I'm good at that. Wow.
Okay, so what I've seen so far is that you're focusing too much on active power only, but there is also reactive power flow in the network. And for congestion, it can be a big difference, you know, if you don't consider the reactive power. So are you considering it because I didn't see you as well?
So the question is, are we also considering reactive power? The short answer is a bit. We never over-effective in reactive power. But also investigation from our equipment department showed that we have close touch for 0.9 years. So it's pretty hard to demand. The generation is actually 1. So there's no reactive power. That's what I mentioned in Sheldon. So yeah, Those values are very using myself.
Yeah, but the power factor of 0.98 could also be, that some of your, the loads could be actually as a capacitor and split other way around further. So it could be that you're not considering that.
Yeah, that might be. So the question was maybe there are some solutions, but we actually have inductance power factor. Yeah, that could be the case. So we're using 0.9 meters and 0.2 in the month. Yeah, that's something else. Until we know better, until we have more information today.
Thank you. My name is Sam. I'm a PhD student at Tijuana Open. I'm running my fourth year. Have a few months ago. So today I'm happy to give a presentation about one part of my work during my PhD, which is fairness incorporated online feedback session for real-time distribution grid measurements. And if you're from Tijuana, it might be familiar because I already gave a presentation 7 months ago. So the outline. So we start with a brief introduction of what kind of issue we are trying to solve on the distribution grid for this specific approach.
Sorry, you have to talk to the microphone.
Yeah, thanks. And then why do we need online feedback compensation, like this specific methodology, and why are we interested in fairness? And then we present some case study results and what kind of conclusion we draw and some limitation in the approach. So I'm showing here like an example picture of a distribution grid that's totally on simulation. You see like green dots, green lines. So basically, if the process is green, it means like the voltage is okay, and if it's yellow, it has some problem. Also for the cables and the transformers. And in this case, we kind of scale the generation by a lot. It's the same bench grid, it's an example grid. And what we're noticing that we have mostly voltage problems locating at the end of the feeders, and we have congestion problem at the beginning of the feeders, and also the transformers. And so the main focus of this approach is to solve voltage problem and also loading problem for the transformer and the cables, and we are focused on the steady state. So a bit of background. So mostly when we talk about optimization, we were referring to this offline model-based optimization. What we mean that we have a representation of the grid in our computer, and we formulate our optimization problem. We solve it. We determine what's the most optimal set point for generators, etc. So this is a model-based approach, and you need a model for the grid. And it's not like raw, it's also like multiple path flow. So you have to code it somehow. And even like the most powerful solver, they have certain limitations that they do not solve every problem to the optimum with guarantees. And so some other motivation we have is that we not always have really precise grid topologies for our distribution system. And most of the model-based approach relies on a load measuring battery to map the load and the generation to voltage and release the voltage to certain limits. And furthermore, it can be computationally very challenging, and people are interested in what kind of model we should use and how we should convex-line, linearize and everything, and about the model exactness and everything. So there's a lot of work there. And also those open loop approaches, see back robustness to disturbances. And I'm showing like the block diagram, and on the top you see what do we mean by the offline optimization. So you start if you look at the box like offline optimization, what you need is a model of the grid. You can assume it's a linear model, whatever. And then you need to estimate the demand. And with the demand and your generation data and your estimate model, you can calculate what's the optimal solution. For example, what's the set point for the generators, etc. And you deploy this decision into the system, and then you have the real demand, disturbance they kick in, and you can observe what's the state of the system, the wide outputs. And this is an open loop system. And on the bottom, you see what we are interested in is online feedback optimization block diagram. And what we have is actually we do not require metering the load. So how the algorithm works is that it observes the system outputs of Y, for example, the voltages, and with this Y, it does some kind of updates of the input, and then given we feed the user system, and we observe what's the Y, what's the new system output is. And I can give you an example with slide. People often use this as an analogy. So, for example, if you want to control your speed in a highway to 100, 130, this open loop system, it feels like you have a model of your car, and you need to know what's the wind speed, what's the friction, what's the weather condition, and everything. And you run this all on the computer, and you calculate how much gas pedal it needs to step in to reach the speed of 100 or 130. And this is what we are doing when you are behind the wheels, right? You don't do any kind of calculation. And what you do is very simple. You observe what the speed is. If it's 99, you might accelerate a little bit. If it's too high, you might slow down a little bit. So you only observe the Y, the speed. You don't really know how heavy is the car, what's the weather condition outside. You're not interested. And to keep the system stable, what you need to do is just you step in a little bit. According to the system outputs and according to system information, which is a linear map between the system output and input, which means if you step in the gas pedal, you know you're going to accelerate, and if you brake, you know you're going to slow down. So then I'm showing a bit model. This one of the applications. It's a lot of equation here. But if you look at it on the left side, we are interested in a case where we have voltage problems and loading problems on the PV generation in the grid. And we are interested in minimizing the curtailment of the PVs. So the capital P can refer to the maximum generation of the PV with irradiance condition. And the Q is the reactive power. And we'd like to minimize curtailment, so minimizing the impact and usage. And at the same time, we have some constraints on the system. We have voltage constraint, we have loading constraint, etc. And we have at the bottom a constraint for the PVs, so we cannot exceed the maximum generation or like the inverter capacity limit. And as you know, we didn't put any relation between voltage and your injection, your PV and your load. So there's no powerful relation in the formulation. And this specific algorithm we did was it's a primary tool method. So we first rephrase this problem into a maximum problem. It's a bit messy here. It's standard optimization technique. You build an optimization procedure, and you have to take in electron, etc. Then, so what I try to show you that the left side and the right side, they are equivalent. That's the optimal solution are the same. So you see, then now we go from a minimization problem to a maximum problem. We have electron, and this specific algorithm is pretty simple. So so it took gradients for the two variable and the primary variable, and it does a gradient descent step, a simple gradient descent step. And for one of the example, if you look at equation 10, there's like a term like a lambda multiplied the voltage minus the maximum voltage. So this is one of the constraints, the voltage constraint that we are interested in. And in a closed loop system, how you use measurements is actually, if you run as an open loop system, you need some kind of evaluation by measuring load. But in this specific case, what you can do is just measure the voltage. You can measure the voltage and do your one gradient descent step to update certain variable. And if this new variable, you do another like gradient descent step to update your new P and Q, so the descent point for the generators. It's a bit hard to explain right now, but the main idea and main message from this slide is that we are interested in minimizing curtailment, and we have a specific algorithm that we kind of incorporate the measurements we have in the system into the control. And the algorithm, as you see, it looks a bit messy, but eventually all the calculations, they are highly decentralized. And on top of that, it's all like very simple operator like class, multiplication, addition, subtraction, etc. So that's a feature. That's a very nice feature. That most calculations are decentralized and it's not very difficult. And even on my laptop for 100,000 iteration, the whole calculation is in less than 2 seconds. And one of the inputs we need for the system are the voltage, the power to voltage. So it means if you check your P, your power, how would that reflect your voltage? And in this case, we use a linear, like a matrix. It maps it how if you change certain power in one node, how much affects the voltage at the other node, and same for the loading. And this is very reasonable because if you are pilot wheels and you don't know if you pressing the gas, you're going to accelerate, and you miss it up, then there's no way you can control the speed of the car. And for this case, we use certain formulation to derive this sensitivity information. And this is for radio grid. And the nice thing that there are a lot of different methods that you can do data-driven method. You can do a simple perturbation on a grid. So the whole algorithm, the whole approach is applicable to all kinds of grid topologies. It doesn't really only apply to radio grids. So with that, I'd like to move to a different, to a second motivation. Why do we need fairness? So with the approach we presented before, what we are able to do, we are able to minimize the period development. We're able to minimize the reactive power compensation and while sticking to the voltage limits and loading limits. And another important consideration we have for the system is fairness. So one of the reasons that for all the buses located towards the end of the feeders, we usually have pretty high sensitivity. And if you look at the diagram on the left side, they have like darker color. So it means that if you consider 1 unit of power, it can like reduce the voltage at other buses more effectively. And this is from the physics of system. And what we did was something pretty simple. And if you are solving this problem in an offline setting, then there are a lot of different things you can do. But in an online setting, to stick to the nice property of this algorithm, what we propose is that they simply modify your matrix. So we say everybody can contribute equally. So this is achieved by modifying this matrix on the left side to the right side. So we force every row to have equal value except for those on 0. So we do not have any impact on other buses. And we do not want to activate that because they have no contribution simply for the sake of fairness. And on the top, you see some of the very preliminary results that if you do not do those fairness consideration, you have the black line. That's the distribution of generation percentage along the feeder from the start to the end. And you notice that the more towards the end, the more the generators are considered. But if you do this fairness design, you're able to achieve the blue line, the blue colors, that everybody will contribute more equally in the sense that they are fair. And in this specific case, we look into the proportionally fair. So it means that all the generators are equal to their maximum generation to their inverter capacity. I'm showing some further results with this specific approach where we apply to controlling the PV generations. So the whole simulation starts with a certain power grid. And if in a real system, we wouldn't need to measure any load because we are simply interested in the system output, the voltage, etc. But since we are running this on the laptop, we actually need a power flow solver. In this case, we use a boundary model. We need a load, and we take some measurements. We feed these measurements into our optimization loop, and we got some new set points for the DRs. And we continue this simulation for iterations. And in this setting, we were previously using power, and now we switch to a power grid model for its higher computational efficiency. So for this case, we run simulation in a second scale, and we need 100,000 rounds of power flow calculation. That really helps us to iterate to tune the hyperparameters. So some of the results, if you just simply focus on one, then like the one on the top on the left side, what we are trying to show that this algorithm converges. So it's the picture might be small, but what we are trying to show is that the active power set point of the generators and all iterations they converge to a certain point. And we compare this to an ideal benchmark when we use then commercial solvers. And what we see that every convergence and it has very similar results compared to like ideal benchmark where we have very accurate with great volatile and we have real-time data measurements. And in terms of fairness, so we did simulation in both balanced case and unbalanced case. And in the balanced case, if you see the top three distribution, you see that that's a distribution of the power generation percentages for different generators located at different places. And what you notice is that in the for the simple case, a linear case, there we do not do any fairness distribution. You see there's a wide range of distribution from like 50% to 100%. That mostly buses located to the ends. They are considered way more than the buses located close to the transformer. And with this specific fairness design, what we're able to do is that everybody was generating around like 82%. And same case goes to the unbalanced case. But there's a little bit different between buses and different physics. This is a physics system. And I was also trying to show that if we look at the voltages, they are actually stabilized as the limits we set, which is 1.05, but the loading of the transformer is also 100%, which is some value set. So on top of that, we also estimation in a dynamic case, which means we are really estimating a time series setting. That while the algorithm takes like 100 or like 200 iterations to converge, in a real system like the low voltage generation, they change pretty fast. We really don't wait for the algorithm to converge. This is a normalized setting. So what we did in the simulation is that every few seconds we have new generation load data, and within each data point we do 1 to 2 updates for the algorithm, and then there's a load change, and we see how this works in the dynamic setting. And here's some of the results we are trying to show. It's quite a lot. If you look at the plot J, so on the top, the second one, what we're trying to show is that you see a lot of like updates, a lot of changing over like days of simulation. But nice thing that if you look at the black line and the red line, the black line is the ideal benchmark which we have. Well, we solve an optimization problem, assuming full information, full great model and everything. And everything really tracks the optimal solution in a very nice way. And if you look at the voltages, it's oscillating stabilized around the 1.05, and the loading is also pretty nicely around 100%. That we are using in full grid capacity, and we are using all of the links for the voltages. Same result we have for the fairness, for the distributional generation that when we do this specific approach has like both generations almost have the same generation, 74%. Yeah, with that I would like to conclude the transition. So the main idea is that we propose a methodology that is a liquid real-time setting that is very fast, that is efficiently decentralized, and it's very scalable because most calculations are done in individual household individual generators. So it's very scalable. It's robust to different services, which we show in the paper. And it's fair and does not, with a very nice problem, it does not need any measurement. Make full use of the and at the same time, there's some limitation of the approach. First, it's really fast and modern communication infrastructure. If you are talking about combination of different DRs in the second cell. And it needs a very fast actuation of the DRs. You need to be able to update the set point in the second cell for whatever you are interested in. And this specific algorithm has a very nice property. It's decentralized, but it also requires a lot of hyperparameter. And on the right, I'm showing a plot. So the basic, so on the y-axis you have the number of iterations the algorithms converge, and on the x-axis is just the more it goes to the right, and larger the step sizes are. So with a very large step size, the risk is that the algorithm is not stable, and with a very small step size, it takes a lot of time to converge. Tracking performance not as good. So that's the trade-off that we use hyperparameter. And it's really a real-time algorithm, and for appliances like offsets across local appliances, and the scaling is So in this case, yes, we are using a model to calculate the sensitivity, the power to voltage sensitivity, but this can be done during cost, etc. So that's one nice feature is that it's really not to have any kind of assumption with its voltage. And we can also use other machine that are more fancier, but then it's also regards to the communication calculation power. And yeah, with that, I want to thank you for your attention, and I'm happy to take any questions.
So it's just ask a simple question. Communication infrastructure. I think this is something for Michelle. I look at my solar inverter. I ask the question to but there are several days of negative price. Then I think, I hope we have a discussion of what do we do with it. To ask the manager, can you block the pulse? Because if you block the pulse, the inverter does not produce power. Even though the sun is shining and then the inverter is full, then it doesn't produce power. First question we got from the inverter vendors that you cannot do that because that function doesn't exist. So can we talk on the inverter? They said that communication protocol doesn't exist. They don't really hold that. In the end, what we have to do is a very minor behavior, switch off the contact from the inverter. This being vice transfer off, until adding that water to the producing. Switch back on and then first again. Where do you see the communication infrastructure goes based on what you want to do? You want to go a second level, second change. It's very easy to convert with the one cycle that is 1 second. How do you see the common language? How can we talk to them? In the transmission system, where IEC 1314 and talk to the SN, SCADA, how do you give your thought?
Yeah, I appreciate the question, but I have to miss this as you also need. Yeah. So, Professor Sun from National is asking a question about how we can have this communication ready for the data. So that's the question.
What is your thought about communication infrastructure? Because
Yeah.
we cannot talk to the SN. All of these does not matter. And if you only talk to one asset, it also doesn't matter that much. You need to have a common language.
Yeah. So the question about, like, for example, what kind of protocols we should have for the communication, and what's my thoughts on the communication part. Well, this has to be some assumption we have for the whole control at second scale. Right now, what's available are the duty control, that everything is local, and they are able to measure the voltage and GPS endpoint. And we assume that those kinds of communication are available for algorithm conversion. I mean, this would be a big assumption and a strong assumption. And personally, I don't really have much background knowledge on how we can actually use this kind of structure. So this is more a exploratory work while we can algorithm actually deploy if we have this kind of communication structure.
I have a question about the slide with the amount of power that's retail. Maybe it's on there if I could use. I would expect that fair algorithm in total produce less power generation because distribute problem. Can you tell something about how big that impact is?
Yeah, so question about like how much, for example, how much extra power is necessary to the it's really depends on individual cases, but the result I've seen is like a 3%. Because like in this setting, for example, the generator, they're only curtailed in this case like 18%. And if it was fairly set in total, maybe costs are feeling like around 5% total. So So it's really a case specific number, and I don't really have a specific number for all different cases. So that's one of the risks. And basically, like some sort of that is that if you write the first families on a large geographic area, so because in that way they have larger difference in the sensitivities. So for example, some of the buses located very close to a transformer, they are closer to the constellation. But if you only enforce values within a small geographic areas, then that would help in reducing the total amount of actual experiment. So it depends on how we want the families to be enforced.
Following from the gentleman, I have a question related to values. First is about active power curtailment. Did you consider reactive power absorption, which can be so other functions of the
Yeah, thanks for foremost last question. Does the algorithm consider reactive power? Yeah. We consider both active and reactive power. And the algorithm is very nicely that's really automatic. We in the constraints test we already defined that reactive power can change according to the maximum jump. So if you see the equation 4, we consider the reactive power to be able to change from due to the only living part of the inverter capacity.
I have another question related to sensitivity metrics. Because normally it's the 5x conjective metrics and it's the static metrics. We know that system state is changing, which we require dynamic metrics instead of static metrics. How did you manage in your simulation if you can update it?
Yeah, the question for hand was the sensitivity matrix. So in this setting, we have the static case, and the sensitivity matrix will be evolving all the time due to load condition and even due to the topological change of the grid. For example, switch is closed or opened. The very nice thing that this algorithm is that because an open is a closed loop system, so it's very robust for some kind of errors we have for the sensitivity matrix. And in the fairness case, we even just modifying those sensitivity matrix and have equal roles, means that every generator contributes equally to vote from and other operator. So the closed loop system makes it very robust. And in our setting, I didn't really changing the sensitivity matrix over time. It's kept the same over time. And there are a lot of researchers who use data-driven methods that they update this sensitivity matrix purely from data and it can be changed over the simulation of the data devices. And of course, the better sensitivity you have, the more accurate you have, the better the performance will be. That you can, in the sense that you can reduce power consumption. But in all cases, the algorithm is able to enforce the force constraint and load constraint, even if you have very horrible sensitivity matrix. So this, for example, in the case that you are behind.
You're talking about the horrible situation, which is the few conditions of the problem for local calculation. So we use Panda power before and now we are using power frequently. So I'm just curious to know for few conditions, normally related to convergence of the protocol calculation. Did you face some challenges there and power grid modeling have to overcome that kind of issue?
Have I what this
these convergences, local calculations?
Yeah, so the question is that convergence solutions are very model. No, actually no. It's only you have.
You are not really facing the new condition of the system, and you see because now we put everything within the bias, right? 1.1 down to 0.9 where you need to have to run the flow with the voltage down to 0.8 and 0.7.
Yeah, only if you scale your generation like crazy to 20 times, then you have very low voltages. And in my case, I think the benchmark is probably something around like 0.9 or 0.92, and we want to bring that to 0.95. And the voltage can go inside 1.8 and we bring that to 1.05. And now, so this is probably still a benign case for power model. And if you scale up to crazy amounts.
Yeah, that's the reason why I'm asking this, because it's linked to long-term voltage and stability problems, which is not in steady state, it's big.
Yeah, you can probably create a test case for Tony, to see if, I think see that. Yes.
I'll from contact us. How could you improve the speed of optimal power flow as battery power flow? I mean, you managed to improve that. Yes.
So what I've been improving is that we replace that power with power model. It doesn't really impact the number of iterations of the output converter because essentially they are both power solvers. What it helps is that power model itself is really way faster than kind of power, and because I have to run hundreds of solid iterations of power model for the algorithm, then that's helps. It's also calculations on policy from the convergence of the optimization.
Yeah, so my question is, in your voltage calculation, you are ignoring the losses. And ignoring those losses can, give you the wrong voltage results. So how much percentage do you think the losses would have impacted your voltage calculation if you didn't ignore the losses? Do you think your result would still be similar if you include the losses there?
Losses.
In your voltage calculation, for example, you're just
So
using the linear losses.
Yeah, so the only input we take is a sensitivity matrix, which is how you map your power change to your voltage change. And in this case, this is a very nice approach for radio grid that you can calculate a sensitivity matrix based on the grid model. And in other settings, that you can also run the whole path flow even at the initial set point, do some perturbation to change a little bit of the P and see how those react. That's also a way of calculating the sensitivity. That way, I think you can include losses. I don't have a specific number that if I use another ways, how much would that affect. What I can say is that it's the very nice thing that it will always enforce the voltage relations and model records. And the better sensitivity model you have, the more accurate it is, then it might, it definitely will reduce the amount of contaminants. And so it helps with the object function design. And I don't have a specific number.
Here's a questions. So it's asked, wherefore utilizes an intermediate iterates as instructions. Does it mean that this will compromise the optimality of the system level computation? Yeah, wherefore utilizes intermediate iterates as instructions. So does it mean that this will compromise the optimality of the system level operations?
So, of course, if you allow the arguments to run like so it's really on the simulation. It depends on what kind of resolution data you have. If you have very low resolution, 50 minutes, then the algorithm runs every few seconds, and also it's converges and checking performance will be perfect. And in real seconds, you assume the load change then a few seconds, and the algorithm can only run a few seconds. That means you have no choice. You only allow the strong iteration before it's going to the next set point. So it's really we try to be practical, not necessarily great mathematician, 15 minutes or whatever. But still, you see that the dynamic saying that the tracking performance is
so you continue the discussion during the board. Oh, yeah.
Thank you. My question is that saying that total power curtail is very variable. So the total power curtail when you are applying this algorithm would change as the topology of the network changes. So you cannot guarantee that there is a particular network would have a particular amount of total power curtailment. So for incorporating fairness, if you are trying to limit the total, can you incorporate or change this algorithm in such a way that you can limit the total amount of power curtailment? by satisfying the fairness factor which you are keeping? Or can you guarantee an upper bound in the or upper bound or lower bound of the total power that is curtailed as the topology of the network changes?
Well, the algorithm so far we designed really all works like automatically. If you have a different topology and different sensitivity, then the algorithm might have a different number of convergence if you have both issues. We did not design that it can only contain say 20%, because that way we might not be able to solve the both problems. And if you somehow define the feasible set, that your P has to be larger than say 80% of the maximum condition, then you might risk that the both problems not solved.
The thing is that if you are avoiding people who are very insensitive to the grid, then you can clearly solve the problem by including a subset of people who are there and then you can carry it.
Yeah, I got the point. So for different end users, you can define that. For example, you can define for some end users we do not do any control. And another way is that we can say that the loop 0, so you do not activate that to loop 0. We have very minimal contribution, and we do not want to set up the event so much just simply for the demos. So it's really a design choice. Okay.
Thank you. Then, now we are reaching the point to also present our also highlights of developments and also come also and then also to some risk on the next section. Thank you. My name is Chris Adamik. I'm the development lead on the program called Meetup. So actually the group that's sitting over here. I'm a scientific software engineer from the Antec, and I have a background in electrical engineering from the theory. And today I will first go through the product model organization itself, how it works. Then go into detail about some highlights the last half year. And afterwards we'll have a brainstorm about new features. So first of all, about project governance itself, we have a technical steering committee of which Tony is the chair. I'm included as well, together with Werner and Jonas, who are not physically here today. And then we have a team of maintainers in the team. Jen and Jerry are here. And Martijn and Jonas, unfortunately not. And then of course there are a lot of developers and contributors from everywhere. So a small reminder of how our community-driven development cycle works. So we have a meetup every half year, so it's in June and in December. And during the meetup, we have a lot of presentations, as you saw, but we also gather feedback from you about a feature request that what should we do in the coming half year. And afterwards, we make a half year roadmap together with the steering committee. And then, of course, we start development on those topics in that half year. And during that half year, we get feedback back from the community. Yes, a new meetup, and so the cycle continues. So I'd like to go through some highlights of the last half year. Some of them will be explained a bit more in detail in the next slides. And some of them will just be mentioned shortly. So we've had two large releases. The first one with short circuit calculations in release 1.5. And then we had the next release with a new serialization format, which I'll explain more in detail in a bit. There's a possibility now to disable settings in state estimation. And we did a hackathon together with the Sunday project. But first of all, I mentioned more in detail in later slides. So that's why I went through them quite fast. Then we have support for C++ now. So in our backend, we use C++. By adopting C++, we can use a lot of new optimization and have a nicer looking code. To put it very bluntly. We have support for Muscle Linux. So what does that mean? It means that you can now also deploy public model in Alpine-based Docker images. We have improved our documentation, both in code documentation as well as the documentation on Meetup. We've also added documentation on the modeling of our components. So for instance, our cables are modeled as a biomodel, the equations are there now as well. So everyone can have a bit more insight on what's happening under the hood. Furthermore, of course, we did some feature improvements and bug fixes. Also thanks a lot to the community for reporting bugs and asking for new features. And we are working on two really large features at this moment. One is an automatic tab changer, and the other one needs reps and state estimation. And in order to be able to implement the automatic tab changer, we needed a really large internal refactor, which is almost finished. We're doing the last task right now. And the mathematical work is finished as well. And then once the refactor is finished, in the beginning of next year, we can actually start with the implementation of it. For neutral reps and state estimation, we also have the mathematical work done. We just started with the proof itself. So it's a different state estimation algorithm, but there will also be opportunity to specify different sigma. So for both B and Q, because well, as a BSO, quite often we measure the power, but not the Q. So well, you can get a different sigma for that one. First of all, there's a nice thing to notify about. We reached 1 million downloads, actually 1.1 already. I have to give a short side note that it does include the automatic downloads from CI. So it's not a million users around the world using Power BI model, but still for us, it felt like a major achievement. Then the first release that we did is 1.5, which we released short symptom calculation. It's a method that's equivalent to the IEC 60909 standard. It's equivalent, not similar. And there are some differences. And the main differences is that the standard does some assumptions to make the calculations easier. But we have the infrastructure ready to do hard calculations. So we don't need to do all assumptions. And also in the standard itself, it's possible to calculate the voltages during a short circuit. But for our method, we are also able to calculate the voltages at the nodes. So if you would like to see what it looks like in our Read Docs page, we have an example. The next one, serialization. So release 1.6. We already had a serialization format for JSON, but there was done in Python. So now we made a way faster implementation in C++. And there are also two possibilities to serialize. So we can load and dump Power BI model data sets both from JSON and message pack.
There are some deprecated functions for the old serialization. So the import JSON data and export JSON data functions are deprecated. So using them. If you are using them, you'll probably get warnings. So they are deprecated right now, and they will be deleted sometime soon. So if you want to see an example on how to use the new functions, there's also an example on our Meetup page. Then it is good to mention that we have a breaking change in the C API in the last half year. And the last meetup we mentioned that we just implemented the C API, which was not stable yet. And indeed, we had a breaking change. It's good to mention that it's not on twice the API, that's stable. And why did this happen? It's because of the dataset concept in the C API. So if any of you were using that, there is a change in the create, update, and calculate function. Also, an example is present if you would like to know more. And then there is another thing that's disabling sensors and status news. It can happen if you, for instance, run a time series that for some moments in time, some sensors will not send anything. So you have missing data. And what did we do? If you, for those sensors that are missing, update the specific sensor for that time instance to an infinite value, and that sensor is easily covered. For that calculation. So if you have enough cells on the neural net, missing out on one, you will eventually calculations. Of course, the more sensors are missing, we can't guarantee that the state estimation will still succeed. 2 weeks ago, we did a hackathon with the Circle project, which is also from LFMG. So we went to for 2 days, and the goal was to build a proof of concept to show that Power can be implemented as a service in the Circle project. We did it together with the Aachen University and PSI Energy. And after 1 day of programming, as you can see, we had a successful proof of concept, and we can conclude that Power Grid model can be integrated with Sunro. So that's something for further development. Then I would like to give a short notification about a workshop for new users. So if you are sitting here or online because you are interested in Power Grid model, but you haven't used it yet yourself, in January 18th, we have a workshop in which we will give more information on how to use Power Grid model, how to perform a power flow calculation, how to use our batch calculation functions, etc. And of course, there will be a lot of time to ask questions as well. So I think the link will be shared through the chat as well, and you can scan your code. Then a notification about deprecation of Python versions. We have a long-term strategy, and that's to support OG3. We are late, so we didn't do that properly in the last year. So currently we support any Python version from 3.8 and up. So for the coming 1.5 years, we will do accelerated adaptation of Python versions, meaning that for each meetup in the coming 1.5 years, we will drop the Python version. So in January, we will launch towards Python 3.8. In July, we will drop 3.9, which is the extra deprecation. Then in January 2025, we'll drop 3.10. From then on, we have 3 versions left, so then we drop 1 version every year. And then we have some community decisions that we need to make. Currently, we support many Linux 2.24. The proposal is to update and support many Linux 2.28. And this might affect some of you, because then the following Linux distributions won't be supported anymore. That's Debian 9, Ubuntu 18.04, and Amazon Linux 2, which includes AWS hosted development platforms. So we'll go into the voting in a bit, where you can specify if it will affect you or not. So we would like to update our sport release distributions, but of course, if there would influence you, we would like to know. I think this one is a bit too short. I have to get to the voting first. So everyone can go to mentime.com and sign in using the code above. The first version is easy. Do you agree to drop many Linux to 24? Yes or no? If the answer is no, you can elaborate it in the next question. So I'll give you a few minutes to set it up.
Yes,
All right, I'll leave it 1 more minute. If there are more votes coming in. I didn't see anything happening anymore. There are some notes. So actually, the next question is more important than this. Then we would like to know why. So if you could elaborate, if you answered no to the last question, please elaborate. We'll wait for a few minutes to get the responses. Solve forward nodes. Waiting for some more answers. All right. Well, thank you for your input. We'll take it into consideration. I see at least 2 comments from our students and we'll in contact with our own colleagues. All right, thank you. And then the next question is actually a brainstorm about new features. So I would like everyone to to join and just put any new feature that you would like to see in Power BI up on the screen. Try to be precise and don't elaborate too much. Afterwards, I'll walk around with the microphone for people if they would like to elaborate their features. Also for the people online, if you would like to elaborate more, feel free to put your elaboration in the chat. If you see something on the screen that wasn't yours, that you really like, you can type exactly the same, and it must become bigger. And we might even implement it earlier. Yeah, that's requests. See, there are still some things popping up in the meetup. I would like to give anyone who would like to elaborate chance to do so. Is there anyone who would like to say something more about the feature request? That's what the slide. So, what will you do after? Okay. So, that's elaborate. Your science engineer, I suppose. All right. Thank you very much for your invitation. I'll leave it open for 2 more minutes so people can still vote. And then afterwards, I would like to hand over the microphone to the team of Alliander, who would like to give a short pitch about some things they are doing inside at Alliander at this moment. They would like to get feedback to be more interested in getting opportunities involved. Yeah, so I'll give this over to Jaap.
Okay, thank you for allowing us to do a short pitch. And it's about one of the feature requests we sent in. Thijs and I, we opened a discussion on the Power Grid forum about one of the packages we are building within Alliander. We are both into data science teams, and we developed a core package we shared between the teams to make developing data science applications easier. So that's already an inner source project at Alliander. In the discussion item, we would like to request your input on whether this is something that would be of use to the Power Grid model community for teams who are not just using the calculation core, but who are also developing more advanced data science applications. So that we try to put a little bit of examples in what the extensions of the package are. So that includes, for example, visualization, which also was one of the feature requests we saw on the brainstorm, but also it makes development easier by some features we added, and it allows for more advanced algorithms, like, for example, graph algorithms. So if you are in a team or in an environment who do more advanced data science analysis using the Power Grid model, please read the discussion and also give your feedback and input on whether it would be useful to add it to the Power Grid model suite. So thank you.
Yeah. Thanks. And Thijs, yeah, will also be at the 3 afterwards. So if you like to have any discussion with them, go grab them. I'll repeat the question and then afterwards we'll repeat the answer as well for the slide. So the question from Irena was, what was the time frame on this? Yeah, so that's very good.
I think it depends a little bit on the scope of possibility to use. Some parts are, I think, more separated with shorter time scale than before. There's two packages. One for maybe a dedicated for that is.
So for people the answers that depends on the scale, there are various things that might be possible. I think doing small increments, it might be possible to implement it quite fast. And if you'd like to do the entire package at once, it might take some more time.
So maybe just to add to that, we listed several features of the package on the discussion page, and maybe people react to it and also comment which of those features they would like to use to get a nice view, maybe debate our priorities on that.
Yeah, so an additional answer is the features, the possible features are listed online in the discussion board. So if you would like any of those features to be implemented and made open source, please specify so in the discussion, and then they can prioritize accordingly. I still have some more minutes before I have to let you know to Tony for the closing. Of course, we'll do the closing later. The viewers will be sure that. But there is some time for questions. So, does anyone have any questions for me at this moment?
There's the question. I can see the reasoning for the visualization. I'm engineer myself, in fact, I also see understanding all of the built in the database. But basically, one of them is it just inherited with data. The question is, in the very short future, do you see it as possible to decouple the modeling part by voice command? Basically, you check the robot, like ChatGPT, then you go on that form. Because it looks like there's a purely database. You have your own API. Through that API to the ChatGPT, will automatically learn. Then build a model of this will work, say, the difference will be 1 to 3. Instead of progression learning the API, I can understand how I can insert the model using the data.
So the question is if we can make something more smart, so for instance, you could use ChatGPT to make it all for you. It's correct. Yeah. Well, of course, it is open source, so probably on ChatGPT here, some old code, so I'm not sure if it's able to hardware or it can be found if you have a relative question, it can be found on all of them. For hardware model itself, it's there's a curve for how to use our API. Also, one of the things that's included in things that advanced computing is actually a bit easier API where you can just add, for instance, one forward to your model and another cable instead of having to really find your entire model if you want to. So that's something that can be included in the data science toolkit or the regular. Any other questions?
Maybe I missed it a little bit, which is solid work out of the inclusion. Like, how can we contribute to the project? Also, how we open the time or so. Can think about that.
As a question is how anyone contribute to the project. So we will go into that just before closing. We'll have a short slide about small ways of contributing. And that's for the time we get a lot of information now we'll make issues for it. So if you find your input back please maybe elaborate a bit more. And then afterwards we will do prioritization. See what will become in the coming half of the year. Another question. Yeah, can you go back to the slide of civilization? Can you elaborate a bit about what is civilization and why is it needed? Yeah. It's interesting in the first person, I have to repeat the question. Power People is an internal data format, which isn't good for saving your data. So, if you would like to save Power People data, you could do some kind of database, but we also made a visualization for easy saving and sharing your data. We have two formats for that. The first one is JSON, which is also really nice and visible. And the second one is message bag, which is a lot faster. So if you would like to save your data somewhere and be able to access it really quickly, you can use message bag. If you would also like to see have a bit better understanding of what your data looks like, if you can save it, you can save it as a JSON. To one last question.
So by saving data, you mean you're saving the array data into JSON or like a for example the nodes, the node array? Is that what you mean by saving the data?
Yeah, so where it will be serialized to the digit format, save the images.
In that case, I would make a feature that maybe for arcade JSON format.
All right, then I'm going to hand over to Tony for some final remarks and closing.
Thank you, Peter, for the nice topic discussions here. So we are very close to the end of this. I suppose everybody is very eager to wait for the drinks and the snacks, so I will keep it short. So what is our goal? So our goal is always to have a community-driven ecosystem. That means although we as Allianz, we take the initiative to develop this project, but this project technically doesn't belong to Allianz anymore. It's a part of Linux Foundation entity. And that means all the people in the Linux Foundation and they can collaborate and contribute, can ask features, report bugs and everything. So think big about working groups, hackathons. We already have done that. Brainstorms. We're definitely going to organize several brainstorms next year with all the topics, like the topics of the data science cookie, visualization, anything. Of course, tutorials, workshops. There will be another workshop the January. But that doesn't mean that only we can organize a workshop. Everybody can organize a workshop. So if you are familiar with Power Model, you can organize a public or private workshop for your organization. That's not a problem at all. Communications. So we use mainly our mailing list for announcements. So please go there to subscribe to the mailing list. And that's a good way to keep updating about the stuff. One caveat is that the lfenergy.org is apparently blocked by many spam users at some companies. So please check regularly your spam email, or maybe even better, give a call to your IT department to make this domain to the whitelist of the mailing list. Roadmap. So we have a roadmap which is also public to everyone with all the defined issues. Of course, that's constantly changing, and also in the roadmap we specify per issue what kind of knowledge is needed to implement this ticket. Is that mainly electrical engineering or C++ knowledge or Python or whatever. So for all the outside contributors, you actually have to get an idea what kind can I do something here or not. Also, issues and discussions. We have a discussion board, so you can always post a new discussions like we just did for the data science cookie. And for a specific bug report or specific feature request on a separate issue, then you can post the issues in the relevant repository. So either the Power Model main repository or the IO repository, or the benchmark or workshop or whatever. So about contributions, that's also answering one of the questions here. To start with, we do not see that you have to be a hardcore programmer to contribute to this project. There are multiple ways of contributing, and we see this. If you are a user of this library, you just use it. You give feedbacks, you report bugs, and that's already a huge contribution to the community. So we value that a lot, and we do listen to the feature requests and bug reports from the community, and try to do proper prioritization about that. And a step further is mainly about validation test cases, and this is a physical calculation model. It has to be validated, otherwise we cannot convince anyone to use it. So if you think you have a new case, in that one case, you want to provide it as a new validation test case to the community, you can always raise a feature request and or upload a validation case. Or if you have a network which you produces very crazy results, you can always upload it to the validation case so we can have a look if that's something wrong. A step further comes with the Python. Many of the, I would say, more than 99% of the users are Python users. So if you think, oh, I think this Python function can be improved, that's documentation can be improved, then you can try to say, oh, then maybe I can submit a pull request to improve the Python API. And eventually, if you're a real hardcore C++ programmer, it's always welcome to contribute to the C++ code with all the new algorithms or models. We have link here, that's the link. Which we believe that's the good position for the first-time contributors to have a look at it. If you're interested to contribute to this project, you can look at it. This view is just a view, a subset of the whole roadmap, which specifies these are the issues might be interesting for the first-time contributor. Yes, that's it. We are reaching the end of this meetup. Any questions regarding the last one? Yes.
I just want to add that for like open source, it's nice to for your own CV as well to contribute to an open source project. So it makes sure because on the other people have and on the other Python account or a GitHub account, for example, I would recommend using your personal GitHub account to contribute to this project. If
So the comments from clients is that by actively participating in open source contributions, that will be possible for the nice items with CV. Hopefully, when you submit or when you apply another data science or software engineering job, and if you use your private GitHub account to contribute, then that will follow as your personal profile. Thank you for the comment. More questions? Also, people online? If not, I would like to close this session. And for the people online, thanks for joining. And we will upload the slides and also the videos later after the session. And for the people on site, let's have some comments and break. Thank you.